Okay, let's dive in. Today we're unpacking a really interesting set of sources, basically a guide for doing empirical research that asks, the big questions.
That's right. It's focused on figuring out cause and effect. What causes what, especially when you can't just run a perfect experiment.
Which is most of the time, right? In the real world.
Exactly. So the main source we're digging into, mostly harmless econometrics, takes a different tack than maybe your standard textbook. It's really about using the data you have to try and mimic that ideal situation, the randomized trial.
Like a medical trial where you randomly give some people the drug and some the placebo.
Precisely that ideal.
Yeah.
Because randomization is the gold standard for figuring out causality. But like you said, we rarely get that luxury.
So this guide, it prioritizes practical stuff, like getting answers you can trust from messy data.
That's the core idea. Practical inference over, let's say, just asymptotic theory. Plus, it's got this unique style, inspired by Douglas Adams, apparently.
Huh. Okay, that's different.
Yeah, simpler math where they can, lots of real-world examples, much more conversational.
So our mission today is to pull out the key ideas from this stack, the concepts, the tools, how researchers try to nail down cause and effect when things aren't so clean cut.
Learning how to make smart comparisons, essentially.
Okay, let's start right there. The causal question. What exactly makes a research question causal, and why is that so important?
Well, a causal question is asking if changing one specific thing directly causes a change in another. It's not just about correlation, like do these things move together. It's does A make B happen?
Like, does going to college cause you to earn more? Or does being hospitalized cause you to get sicker? That last one sounds counterintuitive.
Right, exactly. Those are causal questions. And they're crucial because if we understand causality, we can actually predict the impact of, say, a policy change or an intervention. We know what levers to pull.
And the benchmark we're always kind of mentally comparing to is that perfect experiment, the randomized controlled trial, or RCT.
That's the ideal. Random assignment, randomly putting people into a treatment group or a control group, is powerful because, on average, it makes the two groups identical in every possible way before the treatment happens.
Both the things you can see and the things you can't, like motivation or natural ability.
Exactly. So if you see a difference in outcomes afterwards, you can be pretty confident it's because of the treatment. You're comparing apples to apples. It isolates the causal effect.
The authors have some fun examples, right? Like thinking about hypothetical experiments, even if they're impossible, randomly giving rewards to dropouts.
Or even, randomly assigning government types to former colonies. They joke that one won't get funded.
Yeah.
But these thought experiments, they help clarify what a pure causal effect really means. Even controversial real ones, like the Milgram experiment, push you to think about ideal design, even if flawed.
So thinking experimentally is the goal, even if we can't do the experiment. Because, yeah, the real world isn't random. Which brings us right to the big problem. Selection bias.
Ah, yes. Selection bias. This is probably the single biggest challenge. It happens when the groups you're comparing, say, treated and untreated, were different to begin with, in ways that also affect the outcome you care about.
Okay, that hospital example you mentioned earlier seems perfect. If you just look at data, people who went to the hospital are sicker than people who didn't. The difference is huge.
Yeah.
Statistically significant.
Right, a massive difference. But does that mean the hospital made them sicker? Almost certainly not.
No, it's because, well, people go to the hospital because they're already sick. They selected into the hospital group based on their health.
Precisely. So that simple difference you observe is contaminated. It's a mix of whatever the hospital actually did, hopefully helped, and the fact that the hospitalized group started out much sicker. That initial difference is the selection bias.
The book breaks it down, right? Observed difference, average treatment effect plus selection bias.
Yep, that's the formal way to think about it. The selection bias is that difference in how they would have done even without the treatment, just because the groups were different initially.
And you see this everywhere, like those early studies on job training programs. Sometimes they found people who did the training actually earned less afterward than people who didn't.
Which sounds crazy. But again, think about who signs up for or gets sent to job training. Often it's people who are already having a tough time in the labor market. Maybe their earnings were already low or trending down.
They weren't randomly assigned. They were selected because they needed help. Comparing them to someone who didn't need the program is, well, it's misleading.
Totally. And randomized evaluations of similar programs, like those by Lalonde or Orr, they often found positive effects. The non-experimental result was driven by selection bias.
Same story with class size. Simple comparisons don't show much benefit.
Often, yeah. Because maybe schools put the kids who need more help, the weaker students, into the smaller classes. So again, the groups aren't comparable.
They differ in ways related to the outcome, learning.
Right. But then you have the Tennessee Star experiment, a huge randomized trial, which randomly assigned kids and teachers. And that found clear, lasting benefits from smaller classes.
Okay, so the big takeaway here is fundamental. If people choose or are selected into treatment, just comparing the treated and untreated groups can give you a totally wrong answer because of selection bias. We need ways to fix that comparison.
We need to somehow create or find a situation that mimics that random assignment. We need well-controlled comparisons.
Which leads us to regression, the workhorse you called it.
Absolutely. Regression is probably the most common tool you'll see. The book even has a little anecdote about one of the authors running his first regression back in '79.
Better than being a hospital orderly, he thought.
Definitely. So what regression does at its core is it finds the best line or curve. Sometimes that describes how the average outcome changes when a predictor variable changes. It's trying to approximate the conditional expectation function, or CEF.
So like the average wage for people with 10 years of school, 11 years, 12 years. Regression draws the best line through those averages.
Exactly. Now, how does this help with causality? Well, regression can tackle selection bias if, and this is a big if, the selection bias comes from things you can actually observe and measure.
Okay.
This relies on what's called the conditional independence assumption, or CIA, sometimes called selection on observables.
Break that down. CIA means.
It means that if you can measure and include in your regression all the important variables, the controls or covariates, that determine both who gets the treatment and the outcome, then conditional on those variables, the remaining association between treatment and outcome is causal.
So it's like saying, okay, let's compare people who look identical on all these things I can measure, background, ability, age, whatever. Within those groups, is there still a difference between the treated and untreated?
That's the intuition. You're trying to statistically control for all the observable differences that could be causing selection bias.
Take the returns to education example again. People with more schooling might earn more, but they also differ in other ways.
Right. Family background, maybe innate ability, things like that. So in a regression, trying to estimate the causal effect of schooling on wages, you don't just put in years of schooling. You add controls.
Like parents' education, test scores if you have them, age, race, region.
Exactly. And the book shows what typically happens. When you add those controls, the estimated coefficient on schooling, the estimated return, it usually goes down.
Why?
Because those control variables, like ability scores or parental education, are correlated both with how much schooling someone gets and with their earnings directly. When you omit them, the schooling variable picks up their effect too. That's omitted variable bias. Adding the controls isolates the schooling effect better.
You're stripping away the bias by accounting for those confounding factors you can see.
Correct. It's an attempt to create that apples-to-apples comparison statistically. Matching is a very related idea, using the same core assumption.
How does matching work?
Instead of controlling in a regression, you try to find, for each treated person, one or more untreated people who look really similar on all those observable characteristics. Then you compare outcomes just within those matched sets.
Trying to build a control group that looks just like the treatment group, based on what you can measure.
Yes. And a really clever development related to this is the propensity score.
Ah, right. That sounds useful.
It is. The insight from Rosenbaum and Rubin is that you don't necessarily need to match or control for every single observable characteristic individually. You just need to control for the probability of receiving the treatment, given all those characteristics.
So you predict how likely someone is to get the treatment based on everything you observe about them.
That predicted probability is the propensity score.
And then you compare people who had a similar likelihood of getting treatment, even if some got it and some didn't.
Exactly. You can match people based on their propensity score, or use it as a control variable in a regression, or use it for weighting. The key is, if CIA holds, controlling just for the propensity score is enough to remove bias from all the observed covariates.
That seems much more manageable than trying to match on dozens of variables.
It can be. There was a really influential study by Dehejia and Waba that went back to those job training program results. Remember, Lalonde found non-experimental methods failed to replicate the experimental benchmark.
Yeah, they gave really different answers.
Dehejia and Waba showed that if you used good pre-programmed data and carefully applied propensity score matching, especially controlling for that pre-programmed dip in earnings many trainees had. You could actually get non-experimental estimates much, much closer to the true experimental results.
So, controlling carefully for the observable differences using the propensity score made a huge difference.
It did. It showed the power, but also the difficulty of getting selection on observables right. You need good data on the right variables.
Now, what about when the outcome isn't a nice continuous variable like wages? What if it's like binary employed or not employed? Or a count, limited dependent variables, right? Can you still just run a regression?
That's a great question, covered in Chapter 3.4. You might think you need fancy models like probit or largit for binary outcomes, and sometimes you do for certain questions. But a key point the book makes is that for estimating the average causal effect of a treatment, especially if the treatment itself is binary, like treated, untreated, good old ordinary least squares, OLS regression, often works surprisingly well.
Really, even if the true relationship isn't a straight line.
Yes, OLS still provides the best linear approximation to the underlying conditional mean. And for average effects, that linear approximation can be very close to the true average effect, even if the underlying function is nonlinear.
So the slope from OLS on an O1 outcome can still be interpreted as the change in probability on average.
Pretty much, especially when the treatment variable is also binary. The book shows examples like looking at the effect of having more children on female labor supply, where OLS estimates of the average effect are often very similar to the average marginal effects you'd get from more complicated models like probit. So OLS remains remarkably robust and useful.
That's good to know. Keep it simple when you can. And a quick history note, regression goes way back, doesn't it? Galton and Heights?
Yeah, late 19th century. Francis Galton's studying how kids' heights tended to regress towards the average height. Then Ewell used it for social science, looking at poverty. It's been around.
Okay, so regression and matching are powerful if you can observe and control for the things causing selection bias. But what if you can't? What if the bias comes from unobservable stuff like motivation or true ability or connections?
Now we're getting to instrumental variables, or AV. This is the main tool economists reach for when they suspect selection bias is driven by things they can't measure unobservables.
So AV is for omitted variables you can't put in the regression.
Exactly. The whole idea behind IV is to find some other variable, the instrument, that basically acts like a natural experiment. It creates some sort of random, or at least as if random, variation in who gets the treatment.
Okay, so what makes a variable a good instrument?
Two critical conditions. First, the instrument, let's call it Z, has to be correlated with the treatment. Let's call it X. It has to actually predict or influence whether someone gets the treatment, that's called relevance, or the first stage.
So Z has to push people towards or away from X.
Right. If it doesn't, it's useless. Second, and this is the really tricky one, the instrument Z can only affect the outcome Y through its effect on the treatment X. It cannot have any independent path to Y. That's the exclusion restriction.
So Z influences X and X influences Y, but Z cannot influence Y directly, only via X.
Precisely. If Z affects Y through some other channel, it's not a valid instrument, and the IV estimate will be biased.
Okay, that makes sense. How do you actually estimate the effect using an instrument? What's the intuition?
The intuition is pretty neat. The IV estimate is basically the ratio of two relationships. It's the effect of the instrument on the outcome. That's called the reduced form, divided by the effect of the instrument on the treatment. That's the first stage. Co-YZ over cove X, Z, essentially.
So how much does the outcome change when the instrument changes relative to how much does the treatment change when the instrument changes?
You got it. That ratio gives you the estimated causal effect of X on Y, purging the bias from unobservables that are correlated with X but not Z.
Let's use the classic example, Angrist and Kruger's quarter of birth study, instrumenting for schooling's effect on wages.
Perfect example. Here, the treatment X is years of schooling. The outcome Y is wages. The proposed instrument Z is the quarter of the year you were born in.
How on earth does your birthday affect your wages? Except maybe through schooling.
That's exactly the argument. The link to schooling comes from compulsory schooling laws and school start date cutoffs. Depending on when your birthday falls relative to the school entry date, you reach the legal dropout age at different points in your schooling career.
So kids born, say, earlier in the calendar year might hit the minimum dropout age having completed slightly less school on average.
Exactly. The data shows this. Quarter of birth is correlated with average years of schooling. That's the first stage. It's relevant.
Okay, and the exclusion restriction.
The argument is there any plausible reason why the quarter you were born in would directly affect your adult earnings other than through how much schooling you got.
Yeah.
Most people would say probably not. Maybe some weird seasonal effects on early development, but likely small. So the exclusion restriction seems plausible.
So you look at how wages vary by quarter of birth, reduced form, and how schooling varies by quarter of birth, first stage, and the ratio is the IV estimate of the return to schooling.
That's the logic. The data showed those born earlier in the year had slightly lower schooling and slightly lower wages. The ratio gave an estimate of the causal effect of schooling.
Clever. How do you calculate this in practice? Is it just dividing those two effects?
That works if the instrument is simple, especially binary. That's called the walled estimator. More generally, the standard method is two-stage least squares, or 2SLS.
Two stages. How does that work?
First stage, you regress the treatment variable schooling on the instrument's quarter of birth and any other control variables you want to include. You get the predicted value of schooling from this regression.
Okay, the part of schooling that's explained by the instrument.
Exactly. Second stage, you regress the outcome variable, wages, on that predicted schooling from the first stage and the other controls. The coefficient on predicted schooling in the second stage is your 2SLS estimate of the causal effect.
Got it. Now there's a really important concept with high-V estimates. Late, local average treatment effect.
Yes, absolutely crucial. Late. This came out of work by Imbens and Angrist. The key insight is that an instrument often doesn't affect everyone's treatment status. It only affects a subgroup of the population.
The quarter of birth only affects schooling for people who would have dropped out earlier if they were born in a different quarter. People constrained by the law.
Precisely. These people are called the compliers. They are the ones whose treatment status, how much school they get, is actually changed by the instrument, their quarter of birth. The IV estimate, the 2SLS or walled estimate, doesn't give you the average effect for everyone. It gives you the average treatment effect specifically for the compliers.
So it's a local effect specific to that group induced into treatment by the instrument.
Exactly. That's why it's local.
Hmm.
This interpretation relies on an assumption called monotonicity, which basically means the instrument pushes everyone in the same direction, or not at all. It doesn't make some people get more schooling and others get less.
This seems really clear in, say, randomized trials where not everyone takes up the treatment they were offered.
Perfect example. Suppose you randomly offer people a spot in a program. The offer is your random instrument, Z. Actually participating is the treatment X. The outcome is Y.
Some people offered the program take it, some don't. Some not offered might find a way in any way, though that complicates things.
Let's keep it simple. Offer influences participation. The effect of just being offered the program on the outcome is called the intention to treat effect, or ITT.
Okay, the effect of the offer itself.
Right, but the effect of actually participating for those who only participated because they got the offer, the compliers, that's the ETHI, and you get it by dividing the ITT effect by the difference in participation rates between those offered and not offered the program.
So late ITT compliance rate.
Essentially, yes. The book mentions the Minneapolis domestic violence experiment, where police were randomly assigned to make an arrest or not, but sometimes overruled the assignment. 4V helps estimate the effect of arrest for those cases where the officer complied with the random assignment.
Okay, so IV gives us the effect on compliers. What's this weak instruments problem I hear about?
Big issue. This happens when your instrument Z is only very weakly correlated with the treatment X. The first stage is weak.
Like if quarter of birth barely predicted schooling at all.
Exactly. If the instrument is weak, the 2SLS estimate becomes very unreliable. It gets biased towards the regular OLS estimate, which is biased itself, and its standard errors become problematic. Your results can be all over the place.
How do you know if your instrument is weak?
The common rule of thumb involves looking at the S statistic from the first stage regression. If that F-stat is below, say, 10, a conventional benchmark, you should be very worried about weak instruments.
And what do you do then?
The book suggests practical things. Always look at the reduced form. Does the instrument even predict the outcome? If not, you probably have no effect to find anyway. Also, be aware that different IV estimators, like 2SLS versus another called LAMML, can give different answers with weak instruments. Maybe stick to simpler, just identified models if possible. It's a tricky area. The QOB instrument actually turned out to be somewhat weak in later analyses with more data.
Okay. And what about generalizing late? If it's just the effect on compliers, how broadly can we apply that finding?
That's the external validity question. It's tough. Who are the compliers? Are they representative? Sometimes researchers try using multiple different instruments for the same treatment. These different instruments might have different groups of compliers.
Ah, so if different instruments affecting different groups give similar 5e estimates.
It might suggest the treatment effect is relatively homogeneous across groups, making the late estimate more generalizable. The book mentions a study on family size effects using different instruments that found similar zero effects, suggesting the result was robust. But you always have to think hard about who your instrument is affecting.
Right, context matters hugely. Okay, besides regression and IV, what other design strategies are in the toolkit? You mentioned panel data earlier.
Yes, panel data where you follow the same individuals, or firms, or states, over time opens up other possibilities. The key one is fixed effects estimation.
How does that work?
The idea is to use the repeated observations on each individual to control for any unobserved characteristics of that individual that are constant over time. Things like underlying ability, motivation, maybe family background effects.
So you're using each person as their own control.
Kind of, yeah. But looking at how changes in treatment for that person correlate with changes in outcome for that same person, you difference out any fixed, person-specific unobservables. It's powerful for controlling for time-invariant omitted variables, often used for things like estimating union wage premiums.
Any downsides?
It doesn't control for unobservables that change over time. And it can actually make problems worse if your time-varying variables, like treatment status, have measurement error.
Okay. And differences in differences.
DTE, classic strategy. Usually used for policy evaluation. You need data from before and after a policy change for a group that got the policy treatment group and a similar group that didn't control group.
Like the Card and Kruger minimum wage study. New Jersey raised its minimum wage, neighboring Pennsylvania didn't. Compare employment changes in NJ fast food places to changes in PA fast food places.
Exactly. You calculate the change in outcome in the treatment group, NJ, over time. You calculate the change in outcome in the control group, PA, over time. The difference in those differences is your estimate of the policy's effect.
But it hinges on a big assumption, right? The common trends assumption.
Absolutely critical. You have to assume that, in the absence of the policy change, the outcome variable in both the treatment and control groups would have followed parallel trends. The control group's trend tells you what would have happened in the treatment group without the policy.
And if that's not true, if they were already trending differently,
Then your DDD estimate is biased. The book actually shows a figure using later administrative data for the NJPA study, suggesting the pre-trends weren't perfectly parallel, which complicates the interpretation of the original findings. Checking pre-trends is vital for DD.
And briefly, regression discontinuity, RD.
Another really clever design-based approach. RD exploits situations where treatment is assigned based on whether an individual is above or below some specific cutoff score on a continuous variable.
Like getting a scholarship if your test score is just above 800, but not if it's just below.
Precisely. The idea is that people just above the cutoff and just below the cutoff are likely very, very similar in all other respects, both observed and unobserved. Their treatment status is essentially determined by crossing that arbitrary line.
So it's like a little randomized experiment right around the cutoff point.
Exactly. You compare the outcomes of people just above to those just below. If the treatment probability jumps from 0 to 1 right at the cutoff, it's called sharp RD. If the probability jumps, but maybe not all the way from 0 to 1, like maybe only 50% of those eligible take the scholarship,
It's fuzzy RD.
and fuzzy RD needs 4.
Yes, fuzzy RD is basically an IV setup where the instrument is being above the cutoff and the treatment is actually receiving the scholarship or program. You use the jump in treatment probability at the cutoff to scale the jump in the outcome. Wow. Okay, so lots of ingenious ways to try and isolate causality. All these methods, OLS with controls, 5E, fixed effects, DDRD, seem focused on estimating the average effect of the treatment. But what if the effect isn't average? What if it differs for different people?
Great point. That leads us to quantile regression, which the book covers in Chapter 7. Standard regression focuses on the mean, the average effect. Quantile regression lets you look at the effect of a variable on different points, different quantiles of the entire outcome distribution.
So not just how schooling affects average wages, but how it affects wages for low earners, say the 10th percentile, median earners, 50th percentile, and high earners, 90th percentile.
Exactly that. Instead of approximating the conditional mean function like OLS does, quantile regression approximates the conditional quantile function. It lets you see if the treatment effect is bigger or smaller at different parts of the outcome distribution.
And does it reveal different things?
Oh, absolutely. The book revisits the returns to education example using quantile regression, and the finding is striking.
What did they find?
They found that the effect of an extra year of schooling on wages was not uniform across the wage distribution. And importantly, this changed over time. By the year 2000, the wage boost from more schooling was much larger for people already near the top of the wage distribution, like the 90th percentile, compared to those near the bottom, the 10th percentile.
Whoa, so education was increasing wages more for high earners than low earners, contributing to inequality?
That's what the quantile regression results suggest. It shows how wage inequality was increasing within education groups, not just between them. That's a much richer picture than just looking at the average return.
You wouldn't see that just running a standard OLS regression.
Nope. Quantile regression uncovers heterogeneity in treatment effects across the distribution. You can even combine it with IV to estimate quantile treatment effects for compliers, looking at the effect on different quantiles specifically for that late group.
Fascinating. Okay, so we've spent a lot of time on getting the estimates, the numbers representing the causal effects. But there's another crucial piece. How sure are we about those numbers? Statistical inference, standard errors. The book calls them finite sample bugaboos.
Yes, absolutely vital. Getting the estimate is only half the story. The standard error tells you the precision of that estimate, how much uncertainty surrounds it. If your standard error is huge, your estimate isn't very informative.
And getting the standard error wrong means you might draw the wrong conclusions about whether your result is statistically significant. Right?
Exactly. You might claim an effect exists when it's just noise, or miss a real effect. Standard textbook formulas for standard errors often rely on assumptions that are frequently violated in real-world data.
Like the assumption that the errors, the noise, has the same variance for everyone. Homoskedasticity.
Right. But often, the variance of the errors changes depending on the predictive variables. That's heteroskedasticity.
Mm.
For example, the variation in wages might be larger for high-skilled workers than low-skilled workers. Standard OLS standard errors are wrong under heteroskedasticity.
So you need robust standard errors.
Correct. Robust standard errors, often called white standard errors or Eicher-Huber-White, are designed to be valid even if there's heteroskedasticity. They're essential basically anytime you run a regression.
But the book adds a note of caution.
Yeah, a practical one. In smaller samples, these robust standard errors can sometimes be biased downwards. They can look smaller than they should, making you overconfident. They even note that if the robust standard error comes out smaller than the conventional one, that's a potential red flag.
So what's the advice?
A practical rule of thumb they suggest is calculate both the conventional and the robust standard error, and maybe use the larger of the two for your inference. Be conservative.
Okay, that makes sense. What about the molten problem? That sounds ominous.
It is a significant issue. It arises when you have grouped data. Think students clustered within classrooms, or individuals clustered within states, or repeated observations over time on the same person. Panel data. The errors for observations within the same group are likely to be correlated.
Students in the same class share a teacher, peers, classroom environment. Their random shocks aren't totally independent.
Exactly. If you ignore this correlation and use conventional or even just robust standard errors, you're essentially pretending you have more independent information than you actually do. Your standard errors will be systematically too small, potentially way too small.
You'll think your results are much more precise than they are.
Right. Moulton showed this back in the 80s. The degree of underestimation depends on the group size and how strongly errors are correlated within groups, the intra-cluster correlation. The solution is to use clustered standard errors.
So you tell the software to cluster the standard errors at the level where the correlation is happening, like cluster by classroom or by state.
Precisely. Clustering adjusts the standard error calculation to account for that within-group correlation. It's standard practice now in microeconometrics whenever you have grouped data. Crucial for things like the STAR experiment, cluster by class or school, or DD studies using state-level policies, cluster by state.
Does clustering always fix it?
It helps immensely, but it also has its own requirements. It works best when you have a reasonably large number of clusters. If you only have a few clusters, like maybe only 5 or 6 states in a DD study, then clustered standard errors themselves can be unreliable. Inference with few clusters is another tricky area.
Wow. Okay, so getting the estimate right is hard, and getting the uncertainty around the estimate right is also full of potential pitfalls.
It really is. Sound empirical work requires careful attention to both the identification strategy, how you argue for causality, and the statistical inference, how you assess uncertainty correctly.
Okay, let's try and pull this all together. We've journeyed from the basic problem needing to answer causal questions without perfect experiments through the major hurdle of selection bias.
Which makes simple comparisons so dangerous, like with the hospital or job training examples.
Then we looked at the tools. Regression as the workhorse, trying to control for observable differences using the conditional independence assumption may be helped by matching or propensity scores.
But recognizing its limits when unobservables are the problem.
Which led us to instrumental variables, the search for natural experiments. Those nudges like quarter of birth or random assignment offers understanding that 5e estimates the local average treatment effect, the late, for the compliers.
And being wary of weak instruments.
Then we touched on other designs. Fixed effects using panel data to control for time-invariant unobservables, differences in differences, leveraging policy changes over time between groups, assuming parallel trends.
And regression discontinuity exploiting sharp cutoffs, creating that as-if random assignment right at the threshold.
And we realize effects aren't always average. Quantile regression lets us see how effects differ across the whole distribution, like the widening returns to schooling.
Revealing heterogeneity standard methods might miss.
Finally, we stress the importance of getting the uncertainty right, using robust standard errors for heteroskedasticity, and crucially, clustered standard errors when errors are correlated within groups to avoid the molten problem.
It's all about designing your analysis, choosing the right tool, and being honest about the assumptions and the uncertainty, trying to get as close as possible to that experimental benchmark.
These tools, when used carefully, seem incredibly powerful for uncovering hidden truths, challenging assumptions based on simple comparisons.
They really are. They reveal how selection works, how effects can be localized, how impacts vary. It's about careful, credible detective work with data.
Which brings us to a final thought for you, the listener. The book quotes Douglas Adams, saying rules can help the shape of the problem emerge. How can thinking like this, always asking about the causal question, the comparison group, potential selection bias, the underlying assumptions, help you make sense of the information you see every day?
Yeah, think about the comparisons presented in the news, or in reports, or even in your own work. Are they comparing apples to apples? Could there be selection bias? Is there some hidden natural experiment or cutoff that might offer a cleaner look at cause and effect? Applying this mindset can really change how you interpret the world.